Let's take a look at the following situation. Peter is off and running again. Peter is running on a windy day, running with the wind at his back. It takes him 6 minutes to run a mile. Running against the wind, it takes him 12 minutes to run a mile. If Peter runs equally hard regardless of wind direction, we want to calculate in miles per hour the following. We want to know the wind speed and the speed Peter would run at on a calm day. All right, we've actually seen this, a similar problem to this in a previous application, so we should know how to approach this. First, we want to know that this is a distance problem. Distance equals rate times time, or speed times time. We've used this several times before, so we should be very familiar with it. And let's go ahead, and the first thing we want to do is label our variables. We want to define x, we want to define y. Let's go ahead and let x be Peter's speed. This is the speed that he's running at. And we want to let y equal the wind speed. Now notice we're defining our variables in a very strategic way because it actually answers the questions being asked instead of having to find out some other stuff, do some other work after we find our variables to answer these questions. The A is the wind speed that we want to know, so we're defining the wind speed as y. B is the speed Peter would run at on a calm day, so that's going to be the value of x when y is equal to 0, or when the wind speed is 0. So let's go ahead. Now the first thing we need to do is convert our time units from minutes to hours. They're given in minutes, but we want to know his speed in miles per hour. So we want to convert these minutes into hours. So let's go ahead and do that first. So we have 6 minutes we want to convert into hours. We have 12 minutes that we want to convert into hours. If we divide, there's 60 minutes in an hour, so if we divide 60 by 6, we would get 1/10, or we divide 6 by 60, excuse me. Whenever we're going from a smaller unit to a larger unit, we divide. So 6 divided by 60 is 1/10, 12 divided by 60 is 1/5, but let's go ahead and for now, let's write it as 2/10. And I'll tell you why we did that in a second. All right, now next thing we want to do is we want to take the information we're given here and we want to write a system of equations. All right, so we're given the following information. In 1/10 of an hour, it takes Peter that long to run a mile. He runs a mile in 1/10 of an hour, so we have the distance of 1 and the time of 1/10. So we need an expression to that actually describes Peter's speed. So let's go ahead and write an equation. Let's go ahead and say 1/10, this is our time, times his speed is going to equal 1. Now, how are we going to get Peter's speed when he's running with the wind? Well, his speed is going to be boosted by the wind, so Peter's speed of x is going to be boosted, or we're going to add the wind speed to it. So 1/10 times x plus y equals 1. That's our first equation. Now we know that when he's running against the wind, it takes him 2/10 of an hour. So 2/10 times his speed against the wind equals that same mile. So when he's running against the wind, his speed is going to be hindered by the wind speed. So x minus y will give us his speed. And that's a system of equations that we can now solve. So let's go ahead and do so. Oh, excuse me. Let's go ahead and solve this system of equations. We can start off by distributing this 1/10 and this 2/10 into both the parentheses. So we have 1/10 times x plus 1/10 times y equals 1. And our second equation is 2/10 times x minus 2/10 times y. That equals 1. Okay, so this is our system of equations. We just distributed the fractions into the parentheses, and we want to solve this. We can actually do this very simply by the strategy called elimination. Now we want to have one of the variables in both equations either the exact same or the opposite of one another. Well, here we have our y, the coefficients of our y variables as the opposite signs. We just need to have them as the same fractions, and we left them with the same denominator of 10 for a reason, because what we can do is we can multiply this first equation by a scalar of 2, just a factor of 2, which will give us 2/10 y, and we already have minus 2/10 y here, so when we add these two equations, those two terms will cancel. So let's go ahead and do that. Let's multiply through this equation by 2. So we have 2/10 x plus 2/10 y equals 2 times 1 is 2. And in the second equation, we still have 2/10 x, 2/10 x minus 2/10 y equals 1. Now we can go ahead and add these two equations and eliminate one of our variables. These two terms will cancel, which will give us 2 plus 2 is 4/10 times x equals 3. Now we can go ahead and solve for x. So we have, we can go ahead and simplify this. 4 over 10 is the same as 2 over 5 times x equals 3. And we can multiply by the reciprocal of the coefficient of x, which is 5 over 2, which will isolate x. So we have x on the left-hand side, 5 over 2 times 3 on the right-hand side, so 15 over 2. Or we can also write this as 7.5. 7.5 equals x. X is Peter's speed, so Peter's speed is 7.5 or 7.5 miles per hour. All right, this answers the second question, B. B is the speed Peter would run at on a calm day. And this is actually very intuitive, and we can check this because this is the speed Peter's going to run at when y equals 0. So if we plugged in y for our equation here, or plugged it in here, or plugged it in here, we'll actually get 7.5 miles per hour. So that's when the wind speed is 0. Now we want to know what the actual wind speed is. So we can take this 7.5 or the 15 over 2 and plug it back into either of the original equations and solve for y. We'll get a value for y. So let's go ahead and do that. Let's plug it into the first one since this one involves subtraction. So we have 1 over 10 times x, which is 15 over 2. We have a fraction here, so let's leave this one in fraction form, plus y equals 1. Let's go ahead and distribute this 1/10 in the parentheses. So we have 15 over 20 plus 1/10 y equals 1. We can subtract both sides by 15 over 20. We can move everything to the right except our variable. That's what we want to do. We want to solve for y. These two terms cancel, so we have 1 over 10 times y equals, we can simplify 15 over 20 by writing it as 3 over 4. We just factored a 5 out of the top and the bottom. And we're subtracting it from 1. We can rewrite 1 as 4 over 4. Excuse me, that's a 4 over 4. Now that they have a common denominator, we can combine these two fractions in the next step. So we have 1 over 10 y equals 4 minus 3 is 1/4. Now we can isolate y by multiplying by the reciprocal of 1 over 10, which is 10 over 1. That'll cancel the denominator, just giving us y on the left-hand side. 10 times 1 over 4 is just 10 over 4. Or we can write it in simplest form as 5/2. So y equals the wind speed. So the speed of the wind is 2.5 miles per hour. And that's our second answer, or actually our first answer, A. So the wind speed we found solving the system of linear equations using elimination. The wind speed is 2.5 miles per hour, and Peter's true speed, what he would run on a calm day, or when the wind speed is 0, is 7.5 miles per hour. All right, this was a little more complicated than the previous application because we actually came up with two equations that we needed to manipulate a bit before we can actually use a process of elimination by addition or subtraction, in this case addition. So look over this a few times, make sure you understand how we got from the word problem to the system of equations, and then we should be pretty good at solving them by now. We're just multiplying by a scalar in this example. So I'll see you in the next video.